give people time to get back in. We surprised you. Okay. Well, it's always difficult, but this was especially difficult. I think everyone in the audience gave a question. And they were really good questions. And I would love to go through them all. But obviously we can't. And I've got a bunch here which I hope will take us in an interesting direction. And we may not get through all these because there are some questions for which to answer would have taken the rest of the evening. So I couldn't do those. But there were two questions, Frank. People are fascinated with time, as I know are you.
Yes.
And so basically two questions asking, could time be a medium similar? Could it be a material similar to the man-made idea or is it simply a man-made idea used to understand things? Another person asked, could time be a medium similar to water, silicon? So maybe you want to talk about time. You might even want to mention a kind of crystal.
Yeah. Okay. There are many fascinating aspects to time.
Yeah.
But the narrow question is time a medium? There certainly is a strong sense in which it's a medium. I talked about space as a medium, and in general relativity, or even in special relativity, it's unnatural to separate space and time. The natural thing is space-time, because what looks like space to one person can look like a mixture of space and time to a moving observer, and yet they have equally valid perspectives. So definitely, space is medium, so is time. It's subject to the dynamics of nearby objects. So time slows down near a massive body. This is called the gravitational redshift, and there are other effects like that. Now, inside materials, time can even do funnier things, like. I introduced the concept of a time crystal now about 5 years ago, and this is inside some materials, time becomes a cycle, a circle. It goes back to itself. So that's in essence what a time crystal is. So just as in certain kinds of materials, particles can have funny properties, so can time. Another fascinating aspect of time is that the laws of physics look very accurately the same if you run time forwards or backwards, the fundamental laws, even though everyday life doesn't. But maybe we should not go much further.
I think what people are fascinated by with time is that, as you said, time and space are intricately related, yet you can do circles in space, and at least in the world in which we live, you can't go a circle in time.
Right.
And it seems, therefore, very strange. But the fact that it's malleable,
yes.
The only thing I want to add, which I may have said to this audience at one point or another, is that this time dilation in the presence of gravity is not esoteric at all. It's the reason many of you made it here, because your GPS satellites wouldn't work if we didn't take into account the fact that time on those satellites is different than time on Earth, because they're farther away from the Earth than we are. And that accounts, if we didn't account for that, they'd go out of sync in about a minute. No. So it really is, we have to take into account general relativity every day for you to get to work or wherever you're going.
I'm not sure I mentioned it, but the time crystals have recently been actually discovered experimentally.
So yeah,
that's fun.
There was a question on time crystals, but I thought we didn't have time to do that. I'm going to take this question from Sarah, even though it's a little complicated, but I think it'll allow you and or me to elaborate on how real another way that we understand these quantum fluctuations are real. Mm-hmm. And the question is, can you share how the Casimir force relates to what you were discussing?
Okay.
So
the Casimir force is a famous and rather direct manifestation of the fact that you have quantum fluctuations in space, and that can change the behavior of bodies. So the Casimir effect is if you have two metallic plates, just metallic plates, in empty space, they're electrically neutral. So according to classical physics, there would be no force between them, no electrical force. However, because they change the properties of quantum fluctuations, and there's the quantum fluctuations react back to that. There's an effect, there's an attraction between the plates that's essentially quantum mechanical, and comes from the fact that the calculation derives from the fact that having the plates changes the pattern of quantum fluctuations, changes the energy in a way that depends on distance, and that manifests itself as a force. And now, in recent years, this was predicted, I think, in the mid-1930s, or maybe it was later. But
yeah, it was around 20s or 30s, really early.
Yeah.
It's really amazing.
It was only experimentally observed in recent years, I think in the 21st century, actually.
I think first in very exotic experiments in the 20th century, but now it's
there were indirect
now you can
experiments,
build
yes.
materials that measured all the time.
Now it's become...
And in fact, it's actually for micro materials. I was just at a meeting about this. It's really important because if you have these very thin materials with little wedges in them, it can, you can worry about the Casimir forces affecting the
things get stuck.
Things get stuck.
It's very inconvenient. Things get stuck. So it's become a kind of esoteric branch of quantum engineering to devise shapes and materials that don't get stuck, so you can make micro machines that work.
Well,
so these apparently very esoteric quantum effects are not so esoteric anymore. As technology moves on, what used to be very esoteric becomes actually things we rely on, like time dilation.
Yeah,
and like
exactly. We were
Casimir
taught it every day. And in fact, it gives the whole idea of quantum mechanics a new meaning, because now there are quantum mechanics. It's true. Well, actually, this may answer this question. It's a nice segue into this, because to some extent you've talked about it, but let me just ask it from Albert here. It says, you say that it's possible to create a universe, quote unquote, in 2D by defining the living conditions like silicon. Does that mean it's possible to manipulate that universe's laws of physics? And how would one go about doing it? And I think you were, in some sense, the answer is yes. Maybe you want to elaborate on it.
Yes, well, when we design materials based on the laws we know, we can predict what the properties of physics inside those materials is. So in a sense, we're creating designer universes that have the properties that we predict, and we can manipulate them creatively in order to do useful things, like make anyons and do quantum computing, or make graphene structures that act as sieves, or useful devices. So yes.
Yeah, I mean, in some sense, it's the forefront of technology is literally creating materials whose laws, where the effective laws of physics in that material do what you want them to do, so that they can be useful to technology.
And another extremely important one, the future of the planet, the future of humanity may depend on it, is developing materials that convert the energy of the sun into forms that we can usefully store and use later. That's a frontier of practical physics that's enormously important, because we want to not get away from fossil fuels, use, in principle, the much greater energy raining down on us from the sun. But it has to be done in a way that's economical
and one of the things that's amazing, and it's very
it's
non-intuitive.
All a matter of material science.
Yeah,
right?
but one of the things that has been claimed, and it seems, I think to people like Frank and I, at least seemed highly implausible, but there are apparently experiments that suggest it. Of course, plants do this with photosynthesis, and there have been some claims that actually some sophisticated quantum mechanics, quantum coherence, and other things are related to the process of photosynthesis. It doesn't seem like it should be possible, but it may be.
It may be.
Yeah, I'm skeptical still, but there's some evidence.
This would be entering a technical discussion, but usually, of course, everything is governed by quantum mechanics, but usually there's a fairly strong separation between the operation of chemistry, of quantum mechanics to make atoms and molecules what they are, and the mechanical behavior of the atoms and molecules at room temperatures in messy conditions where the other quantum mechanical effects, other than making the atoms in the first place, are very hidden. So
yeah, it seems like life is a
most of
pretty
us-
messy environment.
Yeah, so like Roger Penrose speculates about quantum effects in the brain, and I think
Everyone
all
who watches-
physicists but one
Yeah,
find that very implausible because it's, you have to go to great lengths in a laboratory to make quantum mechanical effects visible. You have to make things very cold, you have to isolate them and so forth, and the brain is not particularly cold and very messy, and it doesn't seem like the kind of thing where characteristically quantum behavior should be manifest.
Yeah, I mean, it's so hard that's why quantum computers are hard to make, because
Right.
if it was easy, then we'd have one.
We'd all be quantum
Yeah.
computers, right?
Yeah, exactly. We'd all be quantum computers now.
Right.
I'm going to take the easy questions but it's, there's some fundamental questions that I think represent either questions of principle that are worth answering. Does the fact that massless particles, photons, can have mass in a superconductor change the idea that the speed of light is constant? And the simple answer to that is the speed of light isn't constant. We say the speed of light in empty space is constant. But the speed of light in materials is slower than it is in empty space. And of course, in superconductors where photons are massive, it's different still. But in glass and everything else, light slows down. And there are materials now, very fancy materials that people make in the laboratory, where you can actually make light in the material travel at the same speed as you could run.
Yes.
And so the statement that the speed of light is constant is only a statement about the speed of light in empty space. And so there's no contradictions with relativity there, for those who may wonder. And certainly not in the case in superconductors where photons have a mass. Here's a question. Surely it's about anyons. Surely when you say that anyons have memory, this is a useful metaphor, not a statement that fundamental particles have features approaching those of sentient beings. Can you make this explicit? So it might be good for you to
Well,
take that.
it's analogous to saying that transistors have memory, or elementary elements in a computer memory have memory. So the memory of a single transistor or flip-flop, technically, a minimal kind of memory element is very primitive, but you can build it up. It's all a matter of zeros and ones, and if you have enough of them and remember them, that is memory. So the English word memory has kind of two different meanings, or is used very differently. One is to, things that we remember that presuppose a high degree of intelligence and something like a human experience. And then there's the idea of a computer memory, or the more abstract idea of a record is a memory. And the anyons have, of course, the latter, not the former.
Yeah, I wanted to get that question because I'm sure we would hear Deepak Chopra later saying that we said that elementary particles have memory.
Well, it's not altogether
Your
wrong.
friend. Anyway, here's another question related to a confusion that may have come about by a statement like this memory statement from Alexa. Is the ether real? I've heard it is not. However, now I'm confused if it could be. And so, I mean, it goes on, but basically, you might want to elaborate.
It's very real. It's the...
But not in the sense that it was originally, let's be clear,
Well-
not in the sense that it was originally intended. Some
Well-
universal background frame in which you could tell your motion by moving with respect to and things like that.
Well, the ether does not obey the laws of what is called Galilean Newtonian relativity. It obeys the laws of Einstein-Lorentz relativity, but it's really the same. Other than that, it's
Except
it's
you
a
also
space-filling dynamical medium that I think it's the same idea as Maxwell was trying to build models. It's just the mechanics that governs those models has to have the modifications that special relativity.
So the modern
demands.
version of what they were saying, in the old days they said light needed some medium to travel in because it's a wave and waves need
Yes.
some medium. In some sense one would say light are quantum excitations about some medium which is empty
Well,
space.
the electromagnetic,
which is your
electric and magnetic fields. I would say the modern version of the ether is the more abstract version that Maxwell eventually adopted, which is to say, it's a medium made of electric and magnetic dynamical entities we call fields that can fluctuate and support values and support oscillations and so forth. So it's important. I think it's really, Einstein, he's a great man, but he really introduced a lot of confusion here. He did not, the basis of special relativity was not overthrowing Maxwell's ether.
Yeah.
In fact, it was based on Maxwell's equations,
Yeah.
nothing else. So I wouldn't say it was overthrowing the ether, it was refining the notion of what the ether had to be.
Yeah, but
Just
I mean,
like your thing about nothing. It's not that you're, well, I don't know why.
so every now and then me and Einstein confuse people,
Yes,
but it's okay. But I think the key point to stress for people is what isn't true is that there's an absolute rest frame in the universe that you
No,
know.
that's
And that was what was sort of the Michelson-Morley experiment, which discounted that there was that we were all moving, that there was something physical that we were moving in the
think
spectrum.
people thought they knew things about the ether, which in fact are false.
Yeah.
But that doesn't mean there's no ether. It means
Yeah.
that they had false beliefs about the ether.
It just means it's something different than what people thought before, like
Right.
nothing.
Yeah.
Exactly.
Right.
I would claim. Here's a question, which is actually a fascinating question. I'll let you answer it. It's kind of because the answer is yes, but it's really amazing. Can the vacuum be polarized, and what properties of vacuum are discovered that may be new to us? So, the answer is the vacuum is polarized, but maybe you want to go into that a little bit.
Yes. What do we mean by a vacuum being polarized? Well, when we say a material is polarized, we mean something like the following: if you have an electric material that has positive and negative charges, if you put, say, a positive charge here and a negative charge there, then in the material, the negative charges will be attracted to the positive charge, and the positive charges will be attracted to the negative charges. So if you have molecules in there, they'll be slightly distorted with the negatives moving over this way and the positives moving over that way, and we call that a polarization because the molecules are pointing in a certain direction, their electric charge distribution is changed. And in empty space, we have virtual particles. We have virtual, say, electron, anti-electron pairs, one of which is positive and one of which is negative. If you put a positive charge over here and a negative charge over here, those pairs will be polarized. Now the pairs are virtual, so they come to be and pass away in a short amount of time, so the polarization of any one pair doesn't have a permanent effect, but new pairs are popping into existence all the time. So in effect, empty space can be polarized as if it were a material, because it is a material, just as I've been believing. So, and these lead to measurable effects. They change the properties of charges that you put into the vacuum. And in the case of electromagnetism, these are very small effects. But in the case of QCD, this theory of the strong interaction, these effects are very, very large. The medium, the fluctuating, the gluon fields and the quark-anti-quark fields have enormous effects on the color charges that you put in QCD. And calculating those effects, showing that they had physical consequences and checking that, that's what I got the Nobel Prize for. So it's got to be true.
Yeah, well, if you hadn't said it, I would. I was going to leave it at that. But let me make it even. Let me add to that. So, the fact that the vacuum is polarized has been very, very good for Frank, but also for our understanding of nature, and it's really non-intuitive. I mean, it is. When we see an electric charge, we measure the charge in an electron, but we're not measuring the charge in an electron. We're measuring the charge in an electron plus a whole cloud of virtual particles that's around it. And when you pierce that cloud, the charge you see on the electron changes. And it turns out in electromagnetism, the closer you get to an electron, the bigger the charge. And every sensible theory seemed like it would be that way. And the amazing thing that Frank and his colleagues discovered, which they labeled asymptotic freedom, is when you come to a quark, exactly the opposite happens. The closer you get to it, the smaller the charge on it. It's a complicated phenomenon and totally unexpected, was totally unexpected. and is the reason we can understand that force of nature. So that polarization is vital to understanding the behavior of two of the fundamental forces in nature.
Yeah, it's like the Cheshire cat. You go,
Yeah.
There's nothing left when you get close to it. It's just this small.
Okay, so there's, I'm going to take 3 or 4 more questions here because it's getting late, but maybe, and some of them may be long. But one of them will lead us to a different question from Ben. Could the weight and other properties of the vacuum account for dark matter or modified Newtonian mechanics? And the answer is no, but it relates to something else. So why don't you answer? Or maybe you're going to say the answer is it's not responsible for dark matter, but it's responsible for something more
Yes, we have two
interesting.
different concepts called dark matter and dark energy. The dark energy is what Einstein called the cosmological constant. And it has certain properties. It means that space has negative pressure and positive density. And now astronomers have, in fact, measured the density and pressure of space and find exactly that pattern. And not only are they one positive and one negative, but their ratio is predicted by the theory, by general relativity, and that's the ratio that's actually observed. So that's dark energy, and it's a property of space itself, if you like, or of the kinds of things that space itself can support, consistent with the theory of relativity. Dark matter is something else. That's not space itself. That's probably some kind of particle, and probably axions, and it's in principle a distinct phenomenon. There are some wild speculations that maybe the dark matter is some kind of I don't even want they're wild speculations.
They're wild speculations. There's a big difference
discussing.
between.
So we won't discuss them.
Yeah,
right.
The weight of empty space is related to one thing, and it's not related to the dark matter, which is much more.
It seems much
regular,
more conventional.
It seemed pretty exotic when we first talked about it, but
yes.
It's much less exotic than the fact that empty space weighs something, which it appears to do. Yeah. And when empty space weighs something, it blows. It doesn't suck. It's really kind of amazing. So this will lead us. So the way it's phrased is interesting. So Elon Musk has publicly stated that he believes our universe is a simulation, and I will say that people who know more physics than Elon Musk have speculated on that question as well. Although if you're interested, you just may have the opportunity to ask him that question in an upcoming event. But anyway, I don't want to give any. So when you mentioned creating other universes, would these be in our physical space, or are they more like computer simulations? So I want to ask the question: when you think about, indeed, the fact that we engineer materials, then it does automatically occur to people: are we engineered? Is the universe that we live in a simulation, an engineered simulation? And I thought maybe I'd give you a chance to talk about that.
Well, it seems far-fetched. It's a classic mistake to try to explain something in terms of something more complicated. And the laws of physics, as we know them, do not resemble the sort of things that emerge naturally from simple computer programs. They rely on the continuum, that space and time are continuous. They rely on symmetry principles that are very deep. They don't, computer code typically has lots of arbitrary features. If you look at Super Mario worlds, they have laws, but the laws are kind of whimsical, and they don't, they're different at different levels. And so, whereas the laws of physics that we know, you can boil down to very few principles that don't look like computer code. Now, you could ask yourself, what would it look like if the world were a simulation? How would we tell? And in principle, it's very hard to tell. But you would expect maybe that there would be errors occasionally, there'd be missing pixels in the world, or
one maybe
or,
in the White House, but it's
infinite
okay.
loops that go crazy or something. But none of the world just doesn't look like that in any obvious.
But I mean, I think, and there are two things that I guess you elaborate on. But one is that if it was a really perfect simulation, and you couldn't tell the difference, the answer would be it doesn't really matter. We're physicists. We're just trying to figure out how the world works, and whether it's a simulation or not. It doesn't really matter because
this kind of goes back to what we discussed before. This notion of absolute truth. I mean, physics can aspire to absolute truth, but really, that's not what we have or or can get. What we can find is things that are fruitful and work well or not. And so far, the idea that the laws of physics should be formulated as the program of a computer of some recognizable type has not been very fruitful. Right?
Okay, I would agree. And the other thing that you hit, which I think is worth elaborating on, is in some sense it's the same as the question of God. Namely, people who say we need a God to create us don't often ask the question, do you need something to create God? But if you ask, are we a simulation, then you have to ask, as you say, it's not fruitful to talk about something more complicated.
Right.
Were the things that created us a simulation from something else? And if that was the case, does it go on? Is it turtles on the top all the way down? And so the idea of saying we're in a simulation sounds nice, but it begs this huge question of what's the more complicated world that simulated us, and is it a simulation?
Right.
And that
so
doesn't
far,
seem to lead anywhere.
The version of cosmology, physical cosmology, that's proved fruitful and explained actual things about the universe and predicted things successfully and correlates a lot of information, is not based on anything resembling sacred texts that I know of. That doesn't mean that there couldn't be superior beings. It doesn't mean that there could be a God that just let things run this way. But it has not been a fruitful way of understanding the world as we actually observe it.
Let me be a little more specific. People sometimes who like maybe our new Secretary of Education, like to think that maybe evolution is too complicated, that the cells are too complicated to have been created by evolution, so they had to be created by a more complicated being. But then that begs the question, how did that more complicated being come in? If you really want to address these things, it's more useful to think about in terms of simpler things, which you can reduce, which is the way physics has been productive up to now.
I mean, it's not inconceivable that there will be new principles that have to do not with how things have evolved, but what they're evolving to, for instance. This is something that people have speculated about. It's not inconceivable that could explain things, but it hasn't so far.
Yeah. Okay, we'll see if we have the same answer to this one. It's an interesting question, but when we consider that in two-dimensional space, a 3D object is viewed as a cross-section, namely you're viewing a cross-section, and a 3D object moving through that space is just a changing cross-section of that 3D object, then could the images of empty space, that your lava lamp images of empties, point out there's evidence for a fourth dimension, as these objects are just cross-sections in a fourth dimension? And I would say the answer is yes, because in some sense that's what relativity is all about. And as a base, it's already saying that when we see something, it's a slice in a four-dimensional space-time. And so the objects we see are three-dimensional slices of really a four-dimensional space-time, and different observers see three-dimensional slices. And when you put quantum mechanics to that requirement, it eventually results in the kind of quantum fluctuations that you observe. So I in some sense, I'd say that, but I don't know if you have a different take on it.
Well, that as much what you said is certainly valid. I'm not sure that that's what they're asking, but it's certainly valid that the picture we, in practice, get of the world is we take a snapshot at one time, and we take a snapshot at another time, and another time, and another time, And there's a very natural distinction between a whole series of three-dimensional snapshots. But the laws of physics tell us that really all these snapshots are related. Based on one, in principle, you could predict the others. And so they are really cross-sections of a reality that's one dimension higher, space-time. I thought the spirit of the question maybe was more ambitious. Can you understand quantum mechanics as somehow an effect of extra dimensions, perturbing our dimensions? That's an intriguing thought, but again, I don't know how to make useful equations out of it.
Yeah, and to add to that, there's no, this is really important. People for a long time have tried to understand if quantum mechanics was due to something hidden.
Yes.
And we know that no attempt to do that works, and moreover, there are experiments that strongly suggest that any such attempt is likely to fail.
It's definitely difficult, but as you know, some of the most gifted and productive theoretical physicists are deeply skeptical of quantum mechanics. Gerhard at Hooft, which was one of the major heroes of formulating the standard model, does not fundamentally believe in quantum mechanics. He wants to replace it by a deterministic system, which is at least in spirit related to this idea of extra dimensions, having hidden structure that causes the appearance of quantum mechanics from an underlying, more deterministic dynamics. Steve Weinberg has recently expressed skepticism about quantum mechanics.
Well, I want to say Steve, who's another hero of the Standard Model.
Yes.
There's a very good article in this month's or last month's New York Review book called The Trouble with Quantum Mechanics, which gives a really nice description of the problems of trying to go beyond quantum mechanics, combined with his own skepticism. So I think it's a good read to
But for me, I really love quantum mechanics, and I think the way forward is to do more quantum mechanics, not less.
Well, I think quantum mechanics is hard to accept, but Planck said it. I think Planck was the one who said that, physics proceeds one funeral at a time.
Exactly.
And eventually quantum mechanics won't succeed.
We're waiting for Steve and Gerhard.
Yeah. And eventually us. Anyway.
Then everything will be fine.
Yeah, exactly. Okay, the last two questions are somewhat lead us to the realm of maybe metaphysics, which I thought would be better.
I'm sorry about that. They're very good friends.
Yeah.
Couldn't resist.
They're wonderful men. We admire them both.
All right, yes.
Greatly. So someone asked, can nothing exist? And I'm just going to give the answer. What do you mean by nothing? And what we've shown is that your nothing probably isn't really nothing. But so nothing exists. So you want to add something? I figured you might.
Well, there's a line of thought that's frequently invoked in physics called the anthropic argument.
Yeah.
Which is that it's often discussed, in fact, in the context of this idea that there are many different universes, and some of them, and most of them, for instance, that you can imagine, with different kinds of empty space, with different kinds of vacua, it would be very difficult to support intelligent life, or any life at all, or maybe even atoms or structure. So if we want to explain why we don't live in one of those universes, it's easy, because if we lived in one of those, we wouldn't be able to talk about it. And that applies in spades to nothing.
Yeah.
You can explain why there's something rather than nothing, because if there were nothing, we wouldn't be able to talk about it.
Exactly. And I've said that. Sometime in my last book was why is there something rather than nothing. If you could write a book, why is there nothing rather than something? That would be amazing, but you wouldn't be around to write the book, so it doesn't much less sell it. Then the next question is even more specific. I thought these two were interesting, which is, so does the void exist, or has it ever existed? Void meaning absence of space, properties, quantum fluctuations, etc.
Yeah.
And I would say that's above our pay grade. What do you say?
Well, as you may remember, I speculated about that precise thing in a Scientific American article, I believe 1979 or something, a long time ago. There is a notion, okay, so as I elaborated, non-technically I didn't talk about all the nuances, but the idea that space is empty is kind of not on the radar screen in modern physics. Space has all kinds of properties. However, just as fish can imagine taking away the water, we can imagine taking away the Higgs field, taking away all the particles, take away everything that you can, and maybe there's an ideal state that has no condensates, has no particles, has much more symmetry than any other state, and that you would say is, if anything, that deserves to be called nothing. And the speculation was that that state sort of is the only natural starting point for the universe, but it's unstable.
So nothing is unstable.
So nothing is unstable.
Although is that really a void, though, because there are quantum fluctuations?
Well, I told you what it is, and you can call it what you want. But
exactly. It's also in the end. So I think that's the problem when you get to the void, is that it becomes a question. It's in the end of semantics. But what I hope we've made clear is that there are a lot of things we still don't understand, and that the process of trying to understand them is part of what makes life worth living, and it's been a joy to share the evening with one of the people who's worked as hard as anyone to try and understand what we can, and who celebrates openly the fact that there's a lot we don't understand, and the questioning is sometimes as much fun as the answer.
There's a lot we don't understand, and a lot we do understand, and both
worth
are
celebrating.
both great things.
So let's end by celebrating your presence here, and thank you very much. And both Frank and both of us have written books, and I think we're signing them outside for those that have them.
Oh,
but
really?
Thank you again. I think so. We'll go out and find out.
All right.
And thanks for coming, and set your radar for February 25th, and we'll reveal more about that as it happens. And we can't do this without you, and it's always a joy to see the interest and excitement. I thank all of you very much. Thank you.